All right, so looking at this diagram, we have 5 different airports, and each of them are represented by the little dot. But more importantly, every region represents all of the points that are closest to that given airport. So for example, if I'm looking at this region for airport 5, any point within that kind of tan area is going to be closest to airport 5 rather than airport 4 or airport 1, which are the other two closer airports. So these diagrams just segment a big kind of map basically into regions that are closest to one specific point, like airports. And it's an example of a Voronoi diagram. The regions that include the closest points to a given point are named cells. So like this cell or this region for airport 1 would be called a cell. And that airport itself, or the point that you're focusing on, is called a site. The lines between the regions, so all of these straight lines between the regions, are called boundaries or edges. So these diagrams are completed or are formed by using perpendicular bisectors. So you find, so like this line between airport 1 and airport 2, it's the perpendicular bisector of the line that would connect airport 1 and airport 2. We're not going to talk a lot about constructing a Voronoi diagram from scratch. For test purposes, you don't need to know how to construct a full diagram. You just need to know how to use it and maybe complete one that's already been started for you. The point where cell boundaries meet in a diagram is called a vertex. So for example, this point right here, where the perpendicular bisectors between airports 1, 2, 2, 3, and 1 and 3, that point is called a vertex, and it is equidistant from all 3 of those airports. All right, so in example 3, this town has 4 coffee shops at points A, B, C, and D. An entrepreneur wishes to open a new shop in town, but would like it to be as far as possible from the other 4 coffee shops. So we're trying to figure out where should he put it. So we're using this diagram. They give us all the coordinates in case we can't tell from the graph. And they also tell us that each unit represents 1 kilometer. So part A, we're finding the coordinates of the vertices P and Q in the Voronoi diagram. So we're finding the coordinates of these vertices. All right, so the nice thing about that is P, you can easily tell from the graph. You might have to zoom it in a little bit, but you can easily tell from the graph that we're at 5, because it's right along that vertical line, and 3.5, because again, right along that horizontal line. So box it up, because that's good to go. Q is the harder one. Q is not on any grid line. So Q is going to be a little bit more work. To find Q, what we're going to have to do, 3 different things, very similar to the vacuum problem. We're going to have to first find the perpendicular bisector between A and B. So I'm just going to say perpendicular to A and B. Step 2, we'll have to find the perpendicular bisector to A and D. And then part 3, we'll find the intersection of those 2 lines. So again, very similar to the vacuum problem a couple examples back. So that also means that each of these contains those 3 steps as well. We'll have to find the midpoint. We'll have to determine the gradient between the original lines, so between A and B first, and then find the perpendicular bisector using that information. And because we're going to have so much work here, I'm going to condense how much work I actually show, but I'll explain it. So first, finding my midpoint. I have, again, we're in the points up here, so I can just average them up here. So remember, finding the midpoint, you're just finding the average between the x's and the y's. So my average between 1 and 2, between A and B, would be 1.5. And if I average 6 and 2, I'll get 4. Looking at the gradient, I'm just going to say M. Between A and B, you can use the graph if you want to, or you can use the points. If I use the points, 2 minus 6 gets me a -4. 2 minus 1 gets me a positive 1. So the gradient of A to B is a negative 4. But, again, perpendicular, so flipping and negating that, indicate that with the perpendicular, would mean flipping it would be 1/4, negating would be turning it positive. So the real gradient I'm looking for the perpendicular bisector to AB is 1/4. So using, again, the point gradient formula, y minus either using A or B, it doesn't matter. I'm going to use A. So y minus the y value of the point equaling the gradient times x minus the x value of the point. You're going to repeat that exact same process, but now looking between A and D. So finding this green line. All right, so again, same 3 steps. My midpoint I found to be 4.5 and 5.5 from, again, averaging A and D, x's and y's. My slope, I did 5 minus 6 to get negative 1, divided by 8 minus 1 to get 7, so that's where I got the negative 1/7. Flipping and negating, I get a positive 7. And then putting that in my point gradient form to get my equation. So finding the intersection, again, just like the vacuum problem, if you're using Desmos, you do not need to solve for y at all. If you're using the TI, you do need to at least, just in both cases, if you use point A, like I did, at least add the 6 to both sides to get it into y equals form. But you're just finding that intersection point between them. And when you do, and if you round to 3 significant figures, because it's IB, you get the point 4.38 and 4.72. So that is our Q. All right, in part B, determining where a fifth shop should be sited to be as far as possible from any other shop, and determining how far that will be. So we already know that Q and P are equidistant from their 3 closest shops. So Q is equidistant from A, B, and D, and P is equidistant from B, C, and D. So we just need to figure out really which of those 2 shops, because we're limited to the axes that we see or the coordinates that we see. So between P and between Q, which of those 2 should be this new site? So we need to, another 2-stepper, we need to first find the distance from A to Q, or B to Q, or D to Q. If it's equidistant, you can pick any of those 3 points, A, B, or D, and it'll be the same distance to Q as the other 2. So that's going to be step number 1, because that'll get us the distance from any of those 3 points to Q. So step 2 would be to do the same kind of thing, but with P. So we would have to find the distance from B to P, or C to P, or D to P, because again, it's equidistant from all 3 of those shops already. So we just need to find one of those 3 distances. All right, so let's find, for the first one, I'm going to find A to Q, just because alphabetical. But again, it doesn't matter which one you use. So using our distance formula, again, given to you in the formula booklet, I can take the x's from A and Q and subtract them. Doesn't matter the order, because I'm going to square it, plus the difference between the y's squared. And working that in my calculator, I get around 3.62 kilometers. And we can do the same thing for, again, either B to P, C to P, or D to P. I chose to do B to P, so I used the point P with the point B, and when I use the distance formula, I get 3.35 kilometers. So we want this 5th shop to be sited as far as possible from any other shop. So we wanted to find those 2 distances to figure out, well, which one's further, because that'll be the furthest from any other shop. So what this tells me is that the point Q is furthest from any other shop. It's the furthest from the 3 points or the 3 shops that it's already equidistant to, which means it's also going to be further from point C, because look at that distance. So what this tells me is that it should be at point Q. And the distance, because it also asked how far it would be 3.62 kilometers. So that was our final answer.